If you will indulge me, I'm going to have a little bit of fun. I hope you come along and enjoy studying Mars, the last of the 4 inner planets. We're going to play around a little bit. I'm going to do it 2 ways, actually. So we're going to review this in a PowerPoint. I'll show you some pictures, but let's think about it. Let's talk about it. What's going on with Mars? Well, we know which one it is, right? My very excellent mother. So, oh yeah, it's this one right here, isn't it? There's Earth, right? 1 AU, so it's more than 1 AU from Sun. How much more? Well, the key for Mars, the memory aid that I'll give you, and the way of thinking, it's still, all these are the inner planets with iron core and rock mantle and a crust and surface, and maybe they've got an atmosphere, maybe they don't, maybe they got a magnetosphere, maybe they don't, maybe they're active, maybe they're not, maybe they keep their craters, maybe they've covered them. At this point, which worlds are the old surfaces? So, which worlds show the cratering when there were lots of things flying around early in the solar system? Old surfaces haven't changed much. Which 2 worlds were that? And what 2 worlds have we studied here that we've studied that have newer surfaces, that have changed a lot? Okay? And I'm including Moon in that because Mars is kind of an in-betweener. So I say for Mars, it's a world of 1/2 and 2s, or you can think like Mercury was 3s and 1/3, came up a lot. And Mars is 1/2 and 2. Now Mars, as you may know, is the god of war, or one of many gods, right? So the god of war. And the symbol is a shield and a spear. Shield and spear. Again, I don't ask you to remember that in my class, but others might. Now that's, again, the Roman god name. There's a Greek god name. I think you should do a little playing around, so why don't you check that out. 1/2 and 2. And there's a lot of ways that this echoes. So let's take a look, and then again, we'll do a YouTube. So the diameter of Mars, how wide is it? And you can draw it. Make sure you can draw that. Draw circles. We know it's about 1/2 as wide as Earth. Okay, so what does that tell us? It's going to be interesting. Is it still warm inside and active? And what would the surface gravity be like? Let's take a look at this. Remind you of this. You can really think about this. Try to guess. Be bold. It's okay if you're wrong. Sometimes we're surprised. That's kind of cool too. Worlds that are larger stay warm longer, active. Surfaces that cover those craters, newer surfaces. Worlds that are smaller don't stay warm as long. They didn't stay warm long enough to cover up all those craters, except for the Maria, the lava seeping through. Good old Moon and Mercury, Venus and Earth. And where is Mars in all this? Kind of halfway when it comes to size, right? 1/2 as wide. It's a world of 1/2 and 1/2s. We should have a carton of 1/2 and 1/2 here for us. That would be good. It's a world of 1/2 and 1/2. Let's check it out. You could guess a lot with that. All right. So, inside, is it still warm and active? Some. 1/2 and 1/2. Some. How much? We need some missions. Right? We don't expect it to be like Venus, spewing out that carbon dioxide. We don't expect it to be like Earth. Oh, we love Earth. There's an organization, Astronomers for Planet Earth. Check them out. The size, what about the surface gravity? Would it be the same as Earth? Would it be the same as Earth? In similar composition. I'm going to give you a surprise here, but it makes sense. It's about the same as Mercury, which unfortunately is not a half or two. It doesn't always, It's about a third as strong as Earth's. So in a room without a suit, you can jump 3 times higher. I'm still good with that. So a third of Earth's, you can write around 1/3 Earth's. But why? Why would these two things have the same gravity? You know? Remember, this is in closer to sun. Differentiation, a lot of iron. It's got a big iron cannonball in there. It's probably a smaller iron core, right? More rock, less density. Right? So it kind of makes sense. More mass, smaller, different factors. Anyway, kind of interesting. All right, so that's the way it would be on Mars. We could jump in a room like this 3 times higher. That's kind of cool. Just feel lighter. Not as much as on the Moon. So there's that. And how far from Sun? Oh yeah, it's past Earth. So we know what that is. 1 AU, and past it another half of an AU from Sun. So it's farther from Sun than us. And so it's going to be cool to cold surface out there. You're getting pretty far out there. What about motions? Okay. It's got a longer distance to go around once. What's a Mars year? Right? And it's going slower. Kepler's third law, and there's an equation, but we need to have that if you need to. So, orbit, how long? I'll give you a hint. What would be a good guess? About 2 years. 2 Earth years. Let me write that because, Mars, it's 1 year for Mars. 2 Earth years. What's the real number? 1.88. Who cares? Unless you're doing stuff. 1.8 is like 1.9, which is like very close to 2. And we're going to see why that's going to influence your decision to go to Mars. Come back to that. Spin. The Moon was slow in a synchronous spin orbit, 28 days-ish, right? Not quite. 28 days. Mercury, orbiting the Sun, was slow spin. Venus with a slow spin, very slow spin, kind of backwards, just a little bit, right? All these slow spins. Earth is fast. Kind of might think Venus might be fast, right? But it's not. What about Mars out there? What would it be like living on Mars? You could jump higher without a spacesuit. But you got to have a spacesuit when you go outside. It's not months. Mars spins in about 24 and a half hours. That's crazy. 24 and a half hours. It's like Earth. Some say they'll mess with your sleep cycle. So studying and teaching and all that stuff. So 24, you'd have night and day. That's cool. Well, is it tilted? Do we get some seasons out of this? What do you think? Guess. You can look it up. Yes. like Earth. Not exactly, but very close to Earth's tilt. It's very close. Yes, you've got seasons. But they're twice as long. An Earth season is 3 months, 3 months, 3 months, 3 months. You know them well. Now we got 6-month seasons. How about longer? A half and 2, 1/2, 1.5, 2 Earth years, close enough. 24.5. Right, it wasn't quite good for gravity, but that would have been cool. And it's tilted, about the same. Pretty cool. So what's going on? What's happening here? Do you want to go? Maybe I'll leave that for now. I'll leave what that means when we get to missions. So I think that's pretty cool. What's up with Mars? Does it have a magnetosphere? Do the check. So now you know, at this point, we're going to be leaving this, but now you know how to look at worlds and think about these kind of worlds. What's it take for magnetosphere? We need some protection from the solar wind. We get some interesting things here. Boy, if you know this, take some notes, go over it. It's overwhelming, I know, at first, but keep going. You'll see it's just a way of thinking that you get. I mean, we need a hot interior, so we got some liquid iron inside, right? And we need a fast spin. Well, we've got the fast spin, don't we? Not Venus, not Moon, not Mercury, but we got this, like Earth. But it is smaller, isn't it? So it has cooled, hasn't it? Hot liquid iron interior, past? Yes. Go look at the magnetism, send up some missions, yes. Now, not so much. I'll just say no. Why? Because it cooled. Why? Because it's smaller. But it cooled, it took longer to cool. This took longer to cool than Mercury did. Mercury is very hot on the outside, right? Sun is baking the surface, but inside, right, it's solidified. And Moon, out with us, cooled. But this takes longer to cool. These are still warm inside. All right, cool, cool. So the answer is, and that's going to be interesting for this one. And it's really going to be interesting, and somewhere up here I need to talk about this. So let me we'll come back to that. All right, so atmosphere. Well, let's do our checklist. Let's think about what logic would tell us, and then go explore and find out if we're missing something. Gas from out of the hot interior. Well, it was hot. So that informs, and because of size, right? So, okay, was not so much now. Enough gravity to hold? It's weak, right? 1/3 of Earth's. But this one helps, right? Because it's farther away. And so as you get colder out, the gas gets colder. If the gas gets colder, that means it's flying around more slowly. It's not going to tend to fly off. So slower gas, this helps. That helps a lot. It's got some gravity. Everything's got gravity, but it's got, there's 1/3 of Earth's. And this is slower, so that's good. Is it still active? Well, not so much, but maybe. We're exploring. Still some questions. Okay, so a little. got a thin layer of carbon dioxide, carbon and dioxygen, or two oxygens, one carbon, two oxygens. There's a lot of things like that. Silicon, two oxygens, nitrogen, two oxygens, hydrogen, two oxygens, also called water. That stuff. Okay, so this, boy, this size and the distance tells you so much. So that's what's up. We'll take a look at it again. What's going on then with the surface? I mean, it stayed warm long enough to maybe cover some of those craters, right? And it has some processes going on. So let's take a look at the surface features, and then I'll show you. This is just the pre-thinking. And you didn't see what I put up there, did you? Water. So what you find on the surface is a lot. You do have impact craters. You do have volcanic mountains. You do not have tectonic mountains. What else do you have? These throw out boulders, liquid lava, right, that solidifies and cools into blobs to become boulders. You do have an atmosphere, so you see some wind. You have cooling cracks. We'll talk about that. It's a lot of stuff. It's a pretty happening place. And you have erosion. I'll show you some pictures. So the two features, we'll get back to water, remind me, two features by name, I think, give us this half and half of the story of Mars. I mean, this is, as a first pass, this is deep, right? One is a huge volcano. Now, if you've got a lot of heavy gravity, then you start building up the sides and things get pulled down and you have landslides and all that stuff. But if you have weaker gravity, it's easier to kind of build up things because you can imagine they're not going to slide down, not pulled as much. So Olympus Mons is a huge volcano. Check it out. Compare it to Mount Everest. How much taller, how wide. Compare that to a state. Take a look. Huge cooling, Olympus Mons, right? Olympus Mons. And I want to say it one more time, that the Greeks, the Romans, the Greeks, they're not the only story. These are named after their gods, but other people looked up. They saw the dots. People were looking, right? The Incans, etc., Mayans, and then back before, right? So whatever records we have. Oh, who's across the way from Greece? You got Egypt, right? So a lot of cool stuff happening there, and you got Baghdad and all the cool stuff. And people were actually moving around, talking. I don't know how they get around. They didn't have Google Translate. It's kind of wild, actually. But there was interaction, and stuff was brought over, and whatever. But Olympus Mons, Mount Olympus. Might have heard of that Greek. The Olympics. Yeah, there's a connection. Anyway, that's what they named it after. And it's a huge volcano, and that tells us that Mars was hot. Why? Because it's big enough to stay warm. Is it still active? I don't think so. We're doing, we'll see, but I think it's cooled. In fact, as it cooled, as I mentioned with Mercury, when things cool, they contract and they can tend to crack. And so there's a huge crack called Valles Marineris, which is like a pasta sauce to me, and it's a red planet. That's why they named it the god of war. Like, okay, let me finish this thought. It's a huge cooling crack. It has cooled. Half and half. It was hot. It has cooled. Olympus Mons, Valles Marineris. Let me tell you about that. We'll come back to the God of War thing. Knowing this, Mars. Earth. I'll show you a picture. Check it out. Here's my crack. Earth hasn't cooled yet. San Francisco, Washington, D.C., across the U.S. That's how wide that crack is, from there to there. From SF to Washington, D.C. How big is that on here? Across Earth, it's here. Across Mars, it's across much of the face of Mars. Cooling crack. I mean, Grand Canyon is just like a little whatever, right? Compared to this cooling crack, Valles Marineris. Go look at it. Go check it out. See these things, and that's the half and half, right? It was hot because it's bigger. It stayed hot longer, but it has cooled. Earth hasn't cooled yet, but it will. Right? The interior. What do we say for Mars? It was hot, but it has cooled, right? I'll show you some pictures here in a second. Has cooled. That's the theme here. An atmosphere, yeah, thin, a little bit. It's not no, it's not yes, it's in between. So, missions, yeah, it's very, very inviting. Let me not forget to say that. And let me not forget to say that. Okay. So we would like to know if there is life on Mars. Could there be life on Mars? Yes. Definitely there could be life on Mars. Was there life on Mars? We don't know. Is there life on Mars? We don't know. Could there be life on Mars? Yes. So missions, there's just so many missions. There's so many missions. I don't expect people to memorize all this stuff, but just to get a sense of all the missions. I mean, it's so inviting. I know Venus is a little bit closer, but really, do you want to go there? Mars is there. Moon is super close, super close. Right? Mars at its closest is 200 times farther than Moon. Sun is 400 times farther than Moon. 400 times farther. That's 1 AU. Mars at its closest is half AU. Half of 400, 200 times farther than Moon. Okay, missions. So we talk about, there's movies, there's great movies. Lots and lots. And people wondered, is there life? Martians, where are they? Here they are, Martians. We don't see that. Nor do we see buildings or, drop cell phones or, water systems or anything like that. But there are lots. And so, again, remember, it was the late 60s, early 70s of the Apollo missions, and then we started going elsewhere, right? And so what do? Viking 1 and 2, and land there. What do we look for? We're looking for microorganisms. Let's go for it. Let's find microorganisms. Didn't find. Okay, but that's not all you look for. You look for the chemistry, right? You look for what happens when water is present, because we know that water, life likes water, and we find it in crazy places on Earth. So we look for environments where if life started, which we know much more about, how life starts, we know that you can take carbon-based molecules, create intense collision, impact, do it in the lab, and what do you get? Amino acids, the building blocks of life. There are ways to create life, and they seem to happen, but you need an environment for it to take off, right? So we look for it, didn't find it. Another one went up, so there's lots of missions. 90s, Pathfinder, Sojourner Truth, look her up. 03, Spirit and Opportunity, these twin missions. You want water? Well, dig. No. Why dig? There's a crater right there. I already got dug for you. Go down deep, right? So check it out. Very successful, fun little movies you'll see. Lots of orbiters, there. Mars Reconnaissance Orbiter, etc. Curiosity, like this big old truck, biggest thing, landed on Mars. And I think it's interesting when we think about going there. So it left 2011, you have to memorize this, but just to give a sense, how long did it take to go to Mars? About a month is how long Curiosity took. But that's only 8 months. You gotta keep, do you have food in your house for 1 month? I mean, what about water? Well, you get to turn it on, right? We're gonna do that here in a second. So what about water? What about air? What about the whole processes of a biological being? 8 months, wow, maybe. They're working on it, and we're learning a lot about technology and the human body, right? 2018, took 6 months to get there. Launched like earlier in 2018, got there later in 2000, about 6 months. And that was InSight. It's on there measuring to see if it's still active. It's crazy, it picks up little tremors. And they picked up some tremor, there's a little bit, something's going on, a little bit. Not a lot, right, but a little bit. And able to try to figure out more about what's inside. That's what it takes to do the science. That's the hard work. And everybody works on their little bit, so you don't have to know it all. You work hard, but hopefully you enjoy that work. So if you want to do that, certainly talk with me or your professor or whomever, and go for it. You want to be a good musician? Put in the time. So that's a bit about Mars. I'm going to come back here. I will say this one thing. And I'm going to come back here to the question of water. Let me do that. And Mars. Okay, I'll talk about that. I think I'm good. Water. Okay, let me save this. Do you want to go to Mars? Just a model, but check this out. When do you want to go to Mars? Well, should we leave when it's close? Yeah, I mean, it's not super easy to figure this out. There's the path, you can't just drive straight down the road. So we need those laws of Newton and laws of physics and all. But check this out. Let's just keep it simple and say that we're leaving when Mars is close. I mean, when the time is right, when you do all that other stuff. So 1 AU and another half AU. But, again, we don't just drive straight. But we go there and we get there, who knows? Maybe we get there in 6 months. Maybe we improve that and maybe shorten it to 4 months, who knows? So we go up there. Now, remember, we're going faster, right? In fact, we start pulling away, right? So maybe we want to do it here, and we start pulling away. But then